you want to take a slight, not a detour so much as just a slight digression into an alternative approach to computing those values. Okay, so a lot of people, if you've taken 140 or something, or you're prereq to this course, different places, you may have seen some of these alternative approaches to computing variance. So I want to talk about them, and this is not required. You don't need to know these, but I cover them for two reasons. One, these may be the ones that you have seen before and more familiar with, sort of just to connect that with you a little bit. And two, if you do learn these, you can actually, it can help you to speed up your computations, meaning that if on an exam or something, you have a time limit and you're having to compute an ANOVA, knowing these sort of computational versions instead of the deviation versions we've learned before, these sort of more computation, these are like algebraic manipulations that can actually make finding the answers a little faster. So let's talk about those. All right. So here are these are alternatives to the different variance equations we saw before. All right. So instead of the sum of squares total being each score minus the grand mean squared, summed up, right? This is the sum of y squared. So you're going to square each value first and then sum all the squared values. This one up here is sum of y in parentheses is the sum. You're going to sum y first and then square, divided by n. I oftentimes will refer to this as total. And this comes from, the reason why I use total instead of sum y is because I realize, especially like in something like this where it's going to be transcribed, and there was a time when I had, in previous times I've had blind students and I've had deaf students and and there was one class particularly in which I've had both, and that it provided with a sort of extra challenge because I was trying to be more detailed in describing things to the student who was blind, which led to the interpreters there's two deaf students, for the deaf students to work overtime in explaining everything that they could see. So it was a weird combination of trying to find a nice happy medium there. But one of the things I quickly learned in that circumstance was that saying the sum of y squared minus the sum of y in parentheses or whatever, it became sort of difficult to describe that way without it sounding like the same thing. The sum of y squared minus the sum of y squared, right? It's really hard to differentiate that verbally. So what I started to do instead was to say the sum of y squared minus the total squared, which is why there's t here, the total squared over n, and the total and the sum y are the same thing. You just add up all the scores. You get a total for y, total for all your scores. So I typically will use that instead, just because it's just verbally and stuff, it comes out a little better. And when this is transcribed, hopefully it'll help differentiate. So the sum of squares total is the sum of y squared minus the total squared over n. Then you get the sum of squares between groups, where this is the sum of each group, aj, the sum of each group squared. So I'm going to take and sum my group, sum group 1, I'm going to square that number. I'm going to sum group 2, I'm going to square that number. I'm going to sum group 3, and I'm going to square that number. And then I'm going to sum across the three groups. That's why there's two sums. I'm going to sum across the scores within each group, and square each of those sums. And then I'm going to add up all those squared sums for a second sum. That's why it's the sum of aj squared over little n over my individual group n, again minus t squared total squared over n. And then you have the sum of y squared, which is, the sum of squares for within groups, which is the sum of y squared minus the part we just saw in the between groups, which is that sum of aj squared over n. So you see, the reason why this becomes a lot faster to compute is as soon as I compute this or this, they pop up again. So as soon as I compute, say the total squared over n, it pops up again here. So I don't have to compute it twice. As soon as I have something like the sum of y squared, again, it pops up twice. Once I compute the sum of aj squared over n, it again pops up again. So a lot of pieces end up getting recycled, which makes it a lot easier. By the time you get down to this last problem, you don't have to solve for anything again. You already have the pieces, so it's good to make sure and compute each of these parts separately and keep track of them so you can actually reuse them as you go forward. Okay. So these are the equations. Now, one thing I want to note is that under each part of the equations, you divide by the number of scores it took to get the number in the numerator. So, like here, if I'm summing everything up to get a total, that means I summed up n things, big N things, capital N things. So that's why I'm dividing t squared over capital N. But here, the sum of aj, this is the sum of each group. So like in our example, I'm going to sum up the first group, which is the beech nut group, I think. So I'm going to sum the babies in beech nut, which are 5 babies. So I'm going to take, and I'm summing up 5 babies, squaring it. Adding to that, the sum of the next 5 babies squared. Adding to that, the sum of the next 5. So each time I'm adding up 5 things, which is why I'm dividing by 5 things, because that's how many things it took me to get the numbers at the top. Okay, so again, total, took everything, took all the scores, so that's why I'm dividing by capital N. So that's what it says here. Whatever you're adding up on the top, that's what you're dividing by the number of things you added up on top to get the numerator. And so you're going to divide by that number on the bottom. That's what this is talking about here. All right, so let's think about all this stuff. So one thing that helps with using this approach is being provided with some of the information. So if I give you only the means and standard deviations and stuff, then it's probably not going to help you a whole lot. You got to compute a lot of this stuff. But if you're given a setup like this where you have the 3 different groups, the individual scores and things, but you also have the sum for each group already sort of worked out for you, and you have the total and the sum y squared especially. So this sum y squared means I took 3 squared plus 4 squared plus 4 squared plus 4 squared plus 8 squared, 7 squared, 4 squared, 8 squared, 6 squared, 5 squared, 9 squared, 6 squared, 10 squared, 8 squared, 9 squared, all added up to get 673. That's the sum of y squared. The total is just summing 3 plus 4 plus 5 plus 4 plus 4 plus 8 plus 7, like all the way down, right? Each of these sums is the individual group sum. So if I add up these 5 scores, 3, 4, 4, 4, 8, I get 23. If I add up 7, 4, 8, 6, 5, I get 30. If I add up 9, 6, 10, 8, 9, I get 42. All right, so I have the total sum of y squared, plus I have each of the group sums, which makes the rest of this sort of pretty easy to put together. So let's look at how that works. So up here, I need the sum of y squared to get sum of squares total. Sum of y squared minus the total squared over n. So the sum of y squared, we just found it down here, was a 673 number. All right, so 673 minus the total, which down here, if you look, is 95. So that's 95 squared. Right, squared a little bit there. 95 squared, right? 95, looks like a sum now. 95 squared over the total n, which is in this case 15. Okay. So let's figure that out. So what is 95 squared over 15? I'm actually going to solve for the different pieces here. So 673 I already have. So let's take 95 squared. Let's see. 95 squared divided by 15 equals 601,667. All right. So forget about this for 1 second. Let's just think. This is then 673 minus 601.667. If I subtract those, 673 minus 673 minus 601.667 equals 71.333. All right, awesome. So we get the same total sum of squares so far. So if I look here where it says the next one, I have to have another t squared over n. All right, well, I don't even have to do this part to subtract t squared over n. I know that this is 601.667. Means I can put it here too. 601.667 goes there. Already done. I also know that down here, I already have the sum of y squared, so I know that this is 673. So I can shove this here too. 673 goes in there, right? So all those pieces I don't have to even solve anymore. Now, the last piece I do have to solve is the sum of AJ squared. So let's take it piece by piece. So what's sum of AJ mean? So take sum A1, A2, A3. This is sort of a stand-in for each group. I want the sum of each group, and then I'm going to square it. So I'm going to take the sum of group 1, 23. So here's my 23 squared. Sum of the next group is 30. So 30 squared. The sum of the next group is 42. So then I have 42 squared. All right, so 23 squared, 30 squared, 42 squared. And all of that I'm dividing by 5 because 5 is a number in each one of these. It took me 5 numbers to get 23, 5 numbers to get 30, right? So I'm dividing by 5 here. So now I just got to add those up. So 23 squared plus 30 squared plus 42 squared equals, and I'm going to divide that by 5, is 638.6, okay? So that means that this piece, this is 638.6. All right, this whole thing is 638.6. Right? That's what we found. So that means that down here, I don't have to do this again either. All right, I have it here, but I don't need to do it again. It'd be sort of redundant. This is also going to be 638.6. Okay? So now, let's need to do some subtracting, and I'm done. So 638.6 minus 601.667 equals 36.933, which is what we have right here. 36.933, okay? And then at the bottom, 673 minus 638.6 equals 34.4, right? So you get the same sum of squares using this method, and you can avoid all of those deviations, all the subtracting and squaring that we did before. And this makes it a lot faster, especially if you're given the sum of y squared and the total and the sums for the groups. If you're given those numbers, plugging them in here is going to take you a lot less time. So it's a lot less time consuming to find the sums of squares for each of these. Doing this, it helps that pieces get sort of recycled going through, so you can actually reuse pieces once you sort of find them, and it makes things a lot faster. The problem is these equations are not very explanatory or descriptive of what a sum of squares or what a variance is. So it's not very definitional, or, you know, it doesn't really help you to understand what a variance is. They're quick and dirty methods for sort of getting the answer quickly, but they're not very good at sort of helping you understand what a sum of squares, you know, between versus within, all that stuff is actually doing, which is why I focus on those more definitional sort of deviation forms. And those are the ones I want you to know. These are, if you have the extra room, you know, in your memory, and you want to be able to learn this stuff to be faster, then learn these, but learn those first. Learn the deviation forms and understand what they're doing first before trying to do these and sort of save some time. All right.